The paradox of light as time. Welcome. Pause for a moment. Close your eyes and think about distance. When you travel from one city to another, you measure it in kilometers or miles. The distance feels real, tangible, something you can comprehend by the time it takes to drive or fly. But what happens when you try to measure the space between stars? What happens when the distances become so vast that your mind cannot hold them anymore? Have you ever wondered why astronomers stopped using miles and kilometers when they talk about the cosmos, and instead speak in something called light years, a term that sounds like time but describes distance? This paradox sits at the heart of how we understand the universe. A light year is not a measurement of time, despite what its name suggests. It is a measurement of distance, yet it carries within it the concept of time itself. This strange duality reveals something profound about the nature of space, light, and observation. When we measure the universe in light years, we are not simply describing how far apart things are. We are describing how long light takes to travel between those things, and in doing so, we are acknowledging that distance and time are inseparably woven together in the fabric of existence. Think about this. When you look at a star in the night sky, you are not seeing it as it is right now. You are seeing it as it was years, decades, or even centuries ago. The light you receive has been traveling through the vacuum of space, carrying with it an image of the past. Every photon that enters your eye is a messenger from a distant time. This means that observing distance in space is fundamentally an act of observing time. The farther away something is, the older the light you receive from it. Distance and history become the same thing when you measure in light years. Before we begin this journey through the incomprehensible scale of the universe, I would like to invite you to subscribe to the Relaxing Science channel. Give this video a like if the concept intrigues you, and share your location and the time where you are right now in the comments below. Your presence here in this moment is part of the cosmic perspective we are about to explore. You are a conscious being, made of atoms that were forged in the hearts of distant stars, watching other stars from a small planet, orbiting a medium-sized sun. This is the beginning of understanding your place in the vastness. The universe does not measure itself in the units we invented. It does not think in kilometers or miles. It measures itself in the speed at which light travels, and in the time that light takes to cross the void. When astronomers discovered that they needed a new way to describe cosmic distances, they did not create an arbitrary unit. They chose light itself as their measuring stick. They said, "Let us measure distance by how long light takes to cross it." This was not merely a practical choice, it was a philosophical one. It acknowledged that in the cosmos, distance and time are not separate things. They are expressions of the same reality. Throughout this exploration, we will move deeper into what a light year truly means. We will visit the nearest stars and discover that they are not near at all, but incomprehensibly far away. We will learn how looking at distant galaxies is like looking backward through time. We will expand our perspective from our own galaxy to clusters of galaxies, and finally to the observable edge of the universe itself. With each step, the scale will grow and your sense of wonder will deepen. The distances are so vast that the human mind cannot truly grasp them, but we can contemplate them. We can sit with them. We can let them reshape how we understand existence. The act of measuring distance as light travel time also reveals something beautiful about observation itself. When you look at a star that is 10 light years away, you are literally looking at the past. The light left that star 10 years ago and has been traveling through the darkness ever since. In this way, astronomy is not just the study of distant objects, it is the study of history written in light. Every telescope is a time machine. Every observation is a connection across both space and time to a moment that has already passed in the distant cosmos. As we proceed through this journey, you will begin to feel the scale rather than merely understand it intellectually. You will develop an intuition for what it means to live in a universe measured in light years. You will understand why astronomers speak of time and distance as though they were the same thing, because in the context of light, they truly are. The universe is vast beyond comprehension, and yet light connects it all, carrying information and history across the incomprehensible void. This is the mystery we will unravel together one light year at a time, moving from the familiar to the almost impossible to imagine. The journey begins with understanding light itself, the cosmic ruler against which all distance is measured. Before we can truly grasp what a light year is, we must understand what light is, how fast it travels, and why it became the foundation for measuring everything we can see. Light is not simply illumination. It is the fastest thing in the universe, the ultimate speed limit, the cosmic constant that does not change no matter where you measure it or how fast you are moving. It is the thread that connects us to the distant stars and the foundation of all our understanding of space and time. The speed of light as a cosmic constant. In the late 17th century, a Danish astronomer named Ole Rømer made a discovery that would change how humanity understood the cosmos. He was observing the moons of Jupiter, watching as they moved in their orbits with predictable regularity. But he noticed something strange. The moons seemed to move slightly faster or slower, depending on whether Jupiter was closer to Earth or farther away. At first, this seemed impossible. The moons should behave the same regardless of Earth's position. But Rømer realized what was happening. Light was not instantaneous. It took time to travel from Jupiter to Earth. When Jupiter was farther away, the light took longer to reach him, making the moons appear to be slightly ahead of where they should be. When Jupiter was closer, the light arrived faster, and the moons appeared to be where he expected. From this observation, Rømer calculated that light traveled at approximately 200,000 kilometers per second. He was wrong by about 1/3, but he had done something extraordinary. He had proven that light has a finite speed. This discovery was revolutionary. For centuries, philosophers had debated whether light traveled instantaneously or took time to cross space. Now there was evidence. Light moved, and it moved at a specific speed. Over the centuries that followed, scientists refined the measurement. They used increasingly clever experiments to measure light speed more precisely. They bounced light between mirrors. They used spinning wheels and rotating disks. They measured the time it took for light to travel known distances. By the end of the 19th century, scientists had determined that light travels at approximately 299,792 kilometers per second in a vacuum. This number is so fundamental to physics that it is given a special symbol, the letter C, and it is called the speed of light. What makes the speed of light truly remarkable is that it is constant. This is not a poetic statement, it is a physical law. No matter how fast you are moving, no matter what reference frame you are in, light always travels at the same speed relative to you. If you are standing still and measure light speed, you get 299,792 kilometers per second. If you are moving at half the speed of light and measure light speed, you still get 299,792 kilometers per second. This seems to contradict common sense. If you're on a train moving forward and you throw a ball forward, the ball moves faster relative to the ground than it does relative to the train. But light does not behave this way. Light always moves at the same speed, no matter who measures it or from what perspective. This strange property of light is one of the deepest truths about the universe. The constancy of light speed led Albert Einstein to develop his theory of special relativity. Einstein realized that if light always travels at the same speed, then space and time cannot be absolute. They must be relative. They must adjust depending on how fast you are moving. Two observers moving at different speeds will measure different amounts of time passing and different distances traveled, but they will always agree on the speed of light. This insight revolutionized physics. It showed that space and time are not separate things, but rather two aspects of a single entity called space-time. The universe is not a stage on which events occur. The universe is the event itself, a fabric of space and time woven together. For our purposes, what matters is that light speed is constant and well known. We know that light travels at 299,792 kilometers per second. We know this with extraordinary precision. We can use this number to define distance. If we know how fast light travels, and we know how long it takes light to travel from one place to another, we can calculate the distance. This is the foundation of the light year. It is a unit of distance defined by the speed of light and the passage of 1 year. A light year is simply the distance that light travels in 1 year, nothing more and nothing less. To understand the magnitude of a light year, we must first comprehend what 297.92 kilometers per second actually means. Light travels this fast in a vacuum, which is the condition that exists in the space between stars and galaxies. In 1 second, light covers nearly 300,000 kilometers. That is roughly the distance from the Earth to the Moon and back, accomplished in a single second. In 1 minute, light travels approximately 18 million kilometers. In 1 hour, it travels nearly 1.1 billion kilometers. In 1 day, light covers approximately 25.9 billion kilometers. Now multiply that by 365 days, and you begin to approach the distance of 1 light year. 1 light year equals approximately 9.46 trillion kilometers. That is 9,460,000 kilometers, a number so large that it is difficult to hold in your mind. To put this in perspective, the distance from the Earth to the Sun is about 150 million kilometers, a distance we call an astronomical unit. 1 light year is about 63,000 astronomical units. The entire orbit of Neptune, the farthest planet in our solar system, is roughly 30 astronomical units from the Sun. 1 light year would span 1,000 times that distance. The solar system, which seems vast when you think of its planets and their orbits, is actually a tiny speck when measured in light years. What makes light the perfect cosmic measuring stick is that it is the fastest thing in the universe. Nothing travels faster than light. This is not a limitation of our current technology. It is a fundamental law of physics. The speed of light is the universe's ultimate speed limit. Because nothing can travel faster than light, light represents the fastest possible way to carry information across space. When we measure distance in light years, we are measuring it in the most efficient way possible. We are saying, how far would the fastest possible messenger take to cross this distance? This transforms the light year into something more than just a unit. It becomes a statement about the fundamental structure of the universe. The light year also reveals something profound about the relationship between distance and time. Because light always travels at the same speed, distance and time become interchangeable in a sense. If you know how long light takes to travel a distance, you know the distance. If you know the distance, you know how long light takes to cross it. This relationship is so fundamental that physicists often use time as a measure of distance. They might say that something is 1 second away, meaning the distance light travels in 1 second. This way of thinking about space is not just convenient. It reflects the deep truth that distance and time are woven together in the fabric of reality. Distance on Earth versus distance in space. Imagine standing at the edge of a vast canyon. You look across the chasm and try to estimate its width. You might say it is a few hundred meters, or perhaps a kilometer. You can see the far side clearly. You can shout and hear your echo return. The distance is real and comprehensible. Now imagine standing in a desert and looking toward the horizon. The distance to that horizon, where the sky meets the land, is roughly 5 kilometers if you are standing at ground level. You cannot reach it easily, but you know it is there, and you know the distance because you can see it. These are the distances we evolved to understand. Our brains developed to navigate distances measured in tens of meters, hundreds of meters, perhaps a few kilometers. We have intuition for these scales. On Earth, we measure distance in ways that feel natural to us. A meter is roughly the length of a tall person's stride. A kilometer is a distance you might walk in about 10 minutes. A mile is a distance you might drive in a few minutes. These measurements connect to our bodies and our sense of time. When you hear that a city is 100 kilometers away, you can imagine the drive. You know approximately how long it will take. Distance and travel time are linked in your mind. You have developed an intuition for how far things are based on how long it takes to reach them. But space is not Earth. The distances in space are so incomprehensibly vast that all our intuitions break down. Consider the Moon. It orbits Earth at an average distance of 384,400 kilometers. This sounds like a large number, but it is actually close to Earth in cosmic terms. Light takes only 1.3 seconds to travel from Earth to the Moon. The Moon is, in a sense, next door to us. Yet this 384,400 kilometers is so vast that it took humans decades to develop the technology to reach it. It took the fastest rockets we could build, traveling at speeds thousands of kilometers per hour, several days to cross this distance. When you think about it this way, you begin to feel the true scale. Now consider the Sun. It lies 150 million kilometers from Earth. This distance is so vast that it is difficult to comprehend. Light from the Sun takes 8 minutes and 20 seconds to reach us. This means that the sunlight warming your face right now left the Sun over 8 minutes ago. You are always seeing the Sun as it was in the recent past, never as it is in the present moment. The Sun is the closest star to Earth, yet it is so far away that we measure its distance not in kilometers, but in minutes of light travel time. To reach the Sun at the speed of our fastest spacecraft would take several months. To reach it in a car driving at highway speed would take several thousand years. The outer planets of our solar system are even more distant. Jupiter orbits at roughly 780 million kilometers from the Sun. Saturn is at approximately 1.4 billion kilometers. Neptune, the farthest planet, orbits at about 4.5 billion kilometers. These distances are so vast that we have sent robotic spacecraft to explore these worlds, and the signals from these spacecraft take hours to reach us. When we send a command to a rover on Mars, there is a delay of many minutes in each direction. We cannot control the rover in real time. We must send instructions and wait to see if they worked. The distance has introduced a fundamental delay into our communication. Beyond the planets lies the Kuiper Belt, a region filled with icy bodies and dwarf planets. This region extends from about 30 astronomical units to 55 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. The Kuiper Belt is so distant that sunlight takes several hours to reach it. Beyond the Kuiper Belt lies the Oort cloud, a theoretical spherical shell of icy objects that may surround our solar system at a distance of up to 100,000 astronomical units. This is the edge of our solar system, the point beyond which the Sun's gravity weakens and other stars' gravity becomes significant. The Oort cloud is so distant that it would take light weeks to cross it. Yet the entire solar system, from the Sun to the farthest reaches of the Oort cloud, is utterly tiny compared to the distances between stars. This is where our intuitions about distance completely fail. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. This means light from Proxima Centauri takes 4.24 years to reach us. The distance is 40 trillion kilometers. Our fastest spacecraft, the Parker Solar Probe, travels at about 200 kilometers per second, the fastest human-made object ever created. At this speed, it would take 64,000 years to reach Proxima Centauri. 64,000 years. That is longer than the entire history of human civilization. The nearest star is unreachably far. When we measure distance in terms of how long it takes our fastest spacecraft to reach something, we are measuring with a ruler that breaks down immediately when we leave the solar system. We need a new way of thinking about distance. We need a ruler that acknowledges the true scale of space. We need to measure not by how long it would take our spacecraft to travel, but by how long it takes light itself to travel. This is why light years are not just a convenience. They are a necessity. They are the only way to describe the universe in a way that matches its actual structure. The difference between measuring distance on Earth and measuring distance in space is not merely a matter of scale. It is a fundamental shift in how we understand reality. On Earth, distance is something we can traverse. We can walk it, drive it, fly over it. Distance is something we can overcome with effort and time. In space, distance is something that light itself struggles to cross. If light, the fastest thing in the universe, takes years to cross the distance between stars, then that distance is truly incomprehensible to creatures like us, who live our entire lives in a few decades. Distance in space is not something to overcome. It is something to contemplate. It is a boundary that separates us from the cosmos, a reminder that we are bound to this small corner of the universe. What a light year truly represents. Let us now define, with precision and clarity, what a light year actually is. A light year is a unit of distance, not time. This is the most important fact to understand. The name is misleading. It sounds like it measures time, but it measures distance. Specifically, a light year is the distance that light travels through a vacuum in the span of 1 year. To calculate this distance, We take the speed of light, 299,192 kilometers per second, and multiply it by the number of seconds in a year. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365.25 days in a year, accounting for leap years. This gives us approximately 31,557,600 seconds in a year. When we multiply this by 299,792 kilometers per second, we get 9,461,000 kilometers, or approximately 9.46 trillion kilometers. This is 1 light year. It is a distance so vast that it is easier to express it in light years than in kilometers. It is easier to say that something is 1 light year away than to say it is 9.46 trillion kilometers away. To truly grasp what a light year represents, we must think about what it means for light to travel this distance. Light is a wave of electromagnetic radiation. It is made of photons, particles that carry energy. These photons travel at the speed of light in a vacuum, which is the condition that exists in the space between stars. In the space between galaxies, there is almost nothing. There is no air, no dust, no particles to slow light down. Light travels unimpeded at its constant speed. When we measure a light year, we are measuring the path that light traces through this nearly empty space. Imagine a photon leaving a star. This photon is a tiny packet of energy, born in the nuclear reactions at the star's core or produced by the star's hot surface. The photon begins its journey through space, traveling at 299,792 kilometers per second. It travels through the darkness for 1 year, never slowing down, never speeding up. It crosses the void, passing through empty space, occasionally encountering a particle of dust or a molecule of gas, but mostly traveling through nothingness. After 1 year of this journey, the photon has traveled 9.46 trillion kilometers. This is the distance we call a light year. The beauty of defining distance in light years is that it connects distance to time in a profound way. When you say that something is 1 light year away, you are saying that its light takes 1 year to reach you. You are acknowledging that the act of seeing something distant is the act of seeing its ancient light. When you look at a star that is 10 light years away, you are seeing light that left that star 10 years ago. The star you see in the sky is not where it is now. It is where it was a decade in the past. The distance is so great that light itself, the fastest thing in the universe, needs a decade to bridge the gap. This creates a strange and wonderful consequence. When you observe distant objects through a telescope, you are not simply looking at distant things. You are looking at the history of the universe. You are seeing different times at different distances. The nearest stars you see left their light years ago. The distant galaxies you observe through powerful telescopes left their light billions of years ago. When you look at the farthest galaxies, you are seeing the universe as it was when it was very young. You are looking backward through time by looking outward through space. A light year is also a unit that reveals the true meaning of cosmic scale. When astronomers say that the nearest star is 4.4 light years away, they are saying that it takes light more than 4 years to reach us from that star. They are saying that the distance is so vast that light, traveling faster than anything else in the universe, requires years to cross it. This is incomprehensible. This is vast. This is the true scale of space. No spaceship humanity has ever built could make this journey in any reasonable amount of time. No human could survive such a voyage. The nearest star is unreachably far, not because it is far in absolute terms, but because we are small, short-lived creatures in a universe that operates on scales we can barely imagine. The light year also has a philosophical dimension. It represents the fundamental unity of space and time in the universe. In everyday life, we think of space and time as separate things. Space is where things are. Time is when things happen. But in the light year, space and time become one. Distance is measured as time. The farther away something is, the longer light takes to reach it. The distance is not separate from the time. They are the same thing expressed in different ways. This is not merely a mathematical convenience. It reflects the deep structure of reality. Space and time are woven together in a fabric called space-time. The light year is a unit that acknowledges this fundamental truth. When you understand what a light year truly is, you begin to understand the universe differently. You realize that distance in space is not like distance on Earth. You cannot simply travel farther and farther and eventually reach any destination. You can travel farther, but the farther you go, the longer it takes light to reach you from other places. The universe is not a stage with infinite space extending in all directions. It is a structure where distance and time are linked, where seeing is always seeing the past, and where the vast distances between objects are fundamental to their existence. The nearest stars and their hidden distances beyond the solar system, the universe opens up into a realm of stars separated by distances so vast that even the light year becomes a useful measure. The nearest star to our Sun is Proxima Centauri, located 424 light-years away. This star is our cosmic neighbor, our closest stellar companion in the void. Yet this distance means that light from Proxima Centauri takes more than 4 years to reach us. If you were to observe Proxima Centauri right now, you would be seeing light that left the star in 2020. You would not be seeing the star as it is today. You would be seeing it as it was 4 years ago. Proxima Centauri is a red dwarf, a small cool star much dimmer than our Sun. It is so faint that it cannot be seen with the naked eye despite being the closest star to Earth. You could look directly at it and not see it. This is humbling. The nearest star to us is invisible to our eyes. We can only detect it with telescopes, and even then it appears as just another dim point of light among billions. Proxima Centauri orbits in a binary system with 2 other stars, Alpha Centauri A and Alpha Centauri B. These 2 stars are slightly farther away, about 437 light-years from Earth. Together, these 3 stars form the Alpha Centauri system, our nearest stellar neighbors. They are so close that they are gravitationally bound to each other, orbiting around their common center of mass. Yet, they are still light-years apart from us. The next nearest stars are Sirius at 8.6 light-years away and Canopus at 310 light-years away. Sirius is the brightest star in Earth's night sky, easily visible to the naked eye. It appears bright not because it is close, but because it is intrinsically luminous. It is a massive, hot star that produces tremendous amounts of light. When you see Sirius in the night sky, you are seeing light that left the star 8.6 years ago. Canopus is so far away that light from it takes 310 years to reach us. The light you see from Canopus left the star 3 centuries ago, when the United States had just declared independence and the Industrial Revolution was beginning on Earth. As you move farther from the Sun, the stars become more distant. Betelgeuse, a red supergiant star famous for its dramatic color, is approximately 700 light-years away. Its light takes 700 years to reach Earth. The light you see from Betelgeuse left the star around the time the Renaissance was flourishing in Europe. Rigel, another bright star in the constellation Orion, is about 860 light-years away. The light from Rigel that you see today left the star in the year 1160. Deneb, the brightest star in the constellation Cygnus, is approximately 2,600 light-years away. Its light has been traveling through space for more than 2,600 years to reach your eyes. These distances are so vast that human language struggles to express them. We measure them in light-years because light-years are the only unit that makes sense. If we tried to express these distances in kilometers, the numbers would be so large that they would be meaningless. Sirius is 81 trillion kilometers away. Canopus is 2.9 quadrillion kilometers away. These numbers are too large to contemplate. The light year reduces them to something more manageable. But even in light years, the distances are overwhelming. What these distances reveal is that stars are not scattered randomly through space. They are organized in patterns. Our Sun belongs to a stellar neighborhood called the local neighborhood, which consists of stars within about 15 light-years of our Sun. Within this region, there are only about 70 stars, including our own Sun. This might sound like many, but remember that this region is a sphere with a radius of 15 light-years. It is a vast volume of space, and yet it contains only 70 stars. This gives you a sense of how sparse the universe truly is. Stars are not crowded together. They are separated by enormous distances. Beyond the local neighborhood lies the local bubble, a region of low-density interstellar medium extending about 300 light-years from Earth. This region is relatively empty of gas and dust, which is why the stars in our neighborhood are more visible than stars in other regions. Beyond the local bubble, the universe becomes more densely filled with gas and dust, which obscures our view of distant stars. The Milky Way, our galaxy, is organized in a spiral pattern with stars concentrated in spiral arms. Our Sun lies in the Orion Spur, a minor branch of the Sagittarius Arm, one of the galaxy's spiral arms. The stars we see in the night sky, the constellations that humans have named and studied for thousands of years, are all relatively close to us in cosmic terms. They are all within a few thousand light years at most. The famous constellations like Orion, Cassiopeia, and the Big Dipper are visible because their stars are relatively nearby. But beyond these familiar patterns lies an incomprehensibly vast universe of stars we cannot see. Stars so distant that their light has not yet reached us, or stars so faint that no telescope could detect them. The universe is far larger and more populous than what we can observe from Earth. What is remarkable about studying the nearest stars is that it teaches us something fundamental about the structure of the universe. The stars nearest to us are not special. They are not gathered around our Sun for any particular reason. They are simply the stars that happen to be close by. If we could somehow travel to Proxima Centauri and look back at the Sun, we would see it as just another star in the distance. We would see our Sun as a small, yellow star, not particularly remarkable. The universe does not have a center. Every observer in the universe, looking out from their vantage point, sees themselves at the center of an expanding sphere of stars. This is a profound truth about the cosmos. There is no privileged viewpoint. Every location in the universe is equally important and equally ordinary. Seeing into the past through light. One of the most beautiful and strange aspects of astronomy is that observing distant objects is always an act of observing the past. This is not a metaphor or a poetic exaggeration. It is a literal truth. When light travels from a distant source to your eye, time passes. The farther the source, the more time passes. When you look at a star that is 1 light year away, you are seeing light that left the star 1 year ago. When you look at a galaxy that is 1 billion light years away, you are seeing light that left the galaxy 1 billion years ago. You are looking at the universe as it was 1 billion years in the past. This transforms astronomy into something more profound than merely cataloging distant objects. Astronomy becomes the study of cosmic history. Every observation through a telescope is a window into the past. Every discovery of a distant galaxy is a discovery of how the universe looked in its youth. When astronomers point a powerful telescope toward a distant region of space and detect light from galaxies billions of light years away, they are not seeing those galaxies as they are today. They are seeing them as they were billions of years ago, when the universe was much younger. Consider what this means for our understanding of cosmic evolution. When we observe nearby stars and galaxies, we see them as they are relatively recently. But when we observe very distant objects, we see them as they were long ago. This creates a kind of cosmic time machine. By looking at objects at different distances, we can see the universe at different ages. We can observe young galaxies, middle-aged galaxies, and old galaxies all at the same time, because they are at different distances from us. We can watch, in a sense, how galaxies change over billions of years by comparing nearby galaxies with distant ones. The farthest objects we can see are the most distant galaxies, detected by powerful space telescopes like the James Webb Space Telescope. These galaxies are so far away that their light has been traveling through space for more than 13 billion years. When we observe them, we are seeing the universe as it was only a few 100 million years after the Big Bang. We are seeing galaxies when they were young, when they were still forming stars at a rapid rate, when they were fundamentally different from the old galaxies we see nearby. This is not speculation or interpretation. This is direct observation of cosmic history. The concept of seeing the past through light also introduces a profound limitation on what we can know about the universe. We cannot see the present state of distant objects. We can only see their past. If an alien civilization on a planet orbiting Proxima Centauri were to observe Earth through a telescope right now, they would not see Earth as it is today. They would see Earth as it was 424 years ago. If we were to point a telescope at that same alien planet, we would see it as it was 424 years ago. There is no way for us to know what either location looks like in the present moment. The light that carries information about the present has not yet traveled the distance between us. This is not a limitation of our telescopes. It is a fundamental property of the universe. Information cannot travel faster than light. Therefore, distance simultaneity is relative. What counts as now depends on the observer's location. This has profound implications for how we understand reality. It means that the universe does not have a single, universal, present moment. Different observers at different locations in space have different notions of what events are happening right now in the distant universe. This is one of the strangest and most counterintuitive insights of modern physics. It emerges directly from the fact that light takes time to travel across space, and from the fact that light always travels at the same speed, regardless of the observer's motion. The light we observe from distant objects has traveled through billions of years of cosmic history to reach us. That light has passed through the expanding universe, been red-shifted by the expansion, and finally arrived at our telescopes. The light carries within it a record of the universe's history. When we analyze the light from distant galaxies, we can determine their composition, their temperature, their motion through space. We can learn about the universe's past from the light that reaches us. This is why astronomy is sometimes called the most historical of all sciences. It is the only science that can directly observe its subject in the past. The experience of looking at the night sky becomes different when you truly understand that you are looking at the past. When you look at Sirius, you are seeing light that left the star 8.6 years ago. You are seeing Sirius as it was when you were 8.6 years younger. When you look at distant galaxies through a telescope, you are seeing light that has been traveling toward you for billions of years. That light has been crossing the expanding universe, being stretched and redshifted, carrying with it the story of the universe's past. You are not simply observing distant objects. You are touching the past through the medium of light. This creates a sense of connection across time and space that is difficult to put into words. When you observe a distant star, you are connected to it by the light that travels between you. That light is the only thing linking you to that star. It is the only messenger carrying information from that distant place. And because light takes time to travel, you are connected to the star's past, not its present. You are holding a conversation with history, asking the universe to reveal what it looked like long ago, and receiving answers written in the form of ancient light. The Milky Way's incomprehensible span, our home galaxy, the Milky Way, is a vast spiral structure containing an estimated 100 to 400 billion stars. The numbers are so large that astronomers still debate the exact count, but the consensus is clear. There are far more stars in the Milky Way than there are grains of sand on all of Earth's beaches. The galaxy is so large that even measuring it in light years reveals the scale in a way that kilometers cannot. The Milky Way has a diameter of approximately 100,000 light years. This means that light traveling at the fastest speed in the universe would take 100,000 years to cross the galaxy from edge to edge. Our Sun, with all its planets and the entire solar system, is located about 26,000 light years from the galactic center, in a region called the Orion Spur. This means we are not at the center of the galaxy. We are in the outer suburbs, orbiting the galactic core at a distance of 26,000 light years. The galactic center itself is a region of intense activity, home to a supermassive black hole millions of times more massive than our Sun. To comprehend the Milky Way's size, consider that our solar system, which contains the Sun and all its planets out to the Oort cloud, extends only about 100,000 astronomical units from the Sun. An astronomical unit is the distance from Earth to the Sun. The entire solar system is about 100,000 astronomical units across, which is about 0.0047 light years. The Milky Way is about 20 million times larger than our solar system. If the solar system were the size of a marble, the Milky Way would be a sphere larger than the Earth itself. The stars in the Milky Way are not distributed evenly throughout the galaxy. They are concentrated in a spiral disk with a thick bulge at the center and spiral arms extending outward. The spiral arms are regions where stars are more densely packed. These arms rotate around the galactic center, taking about 225 to 250 million years to complete one full rotation. Our Sun orbits the galactic center at a speed of about 230 kilometers per second. At this speed, it takes our Sun approximately 225 million years to complete one orbit around the galactic center. This period is sometimes called a galactic year or cosmic year. Since the Sun formed about 4.6 billion years ago, it has completed about 20 orbits around the galactic center. The Milky Way also contains vast regions of gas and dust called nebulae. These regions are the birthplaces of stars. When gravity causes the gas and dust to collapse, stars form. Some of these regions are illuminated by nearby stars and appear as colorful clouds in telescopes. Others are dark, obscuring the light from stars behind them. The Orion Nebula, one of the most famous stellar nurseries, is about 1,350 light-years away from Earth. It is a region where new stars are actively forming, creating a spectacular display of light and color. The size of the Milky Way was not always known. For most of human history, people did not even know that the Milky Way was a galaxy. They saw it as a cloudy band of light stretching across the night sky, which is where it gets its name. In the early 20th century, astronomers debated whether the Milky Way was the entire universe or just one of many galaxies. In 1924, Edwin Hubble made observations of Cepheid variable stars in the Andromeda Nebula and determined that it was actually a separate galaxy far beyond the Milky Way. This discovery revealed that the universe was far larger than anyone had imagined. The Milky Way was not the universe, it was just one galaxy among billions. Within the Milky Way, distances are so vast that light itself takes thousands of years to cross them. If you were on a star on the opposite side of the galaxy from Earth, the light from our Sun would take 50,000 years to reach you. That is longer than the entire history of human civilization. The galaxy is so large that it is essentially impossible to travel across it. Even if we could somehow travel at the speed of light, which physics tells us is impossible for massive objects, it would take 100,000 years to cross the galaxy. For creatures like us who live only a few decades, the Milky Way is effectively infinite. Yet the Milky Way is not unique. It is one galaxy among billions of others in the observable universe. Some of these galaxies are larger than the Milky Way, some are smaller. Some are spiral galaxies like the Milky Way. Others are elliptical, shaped like stretched spheres. Still others are irregular, with no particular shape. The Milky Way is a large galaxy, but it is not the largest. It is a typical large spiral galaxy, neither extraordinary nor unremarkable in the cosmic scheme. The Milky Way's span in light years reveals something profound about the structure of the universe. Within a single galaxy, there are distances so vast that light itself takes tens of thousands of years to traverse them. This is within a single galaxy. The spaces between galaxies are even vaster. When you understand the size of the Milky Way measured in light years, you begin to appreciate the true scale of the cosmos. You begin to understand why astronomers need units like light years to describe space. Kilometers and miles are utterly inadequate. Even the astronomical unit, the distance from Earth to the Sun, is too small to be useful. Only the light year captures the true scale. Beyond our galaxy, the Andromeda Revelation. Beyond the Milky Way lies another great galaxy, the Andromeda Galaxy, also known as M31, or the Andromeda Nebula. Andromeda is the nearest large galaxy to the Milky Way, and it is also one of the most distant objects visible to the naked eye. You can see Andromeda without any optical aid, if you know where to look and if the sky is dark enough. It appears as a faint, elongated smudge of light in the constellation Andromeda. To the naked eye, it looks like a small cloud, but telescopes reveal its true nature. A massive spiral galaxy containing about 1 trillion stars, roughly 3 times as many stars as the Milky Way. Andromeda is 2.5 million light-years away. This distance means that the light from Andromeda that you see today left the galaxy 2.5 million years ago. When that light began its journey toward Earth, human beings had not yet evolved. Our ancestors were still living in Africa, just beginning to walk upright. The light has been traveling through the expanding universe for 2.5 million years to reach your eyes. This is the most distant object visible to the naked eye, yet it is still relatively close in cosmic terms. The distance to Andromeda reveals something striking about the scale of space. The Milky Way and Andromeda are the two largest galaxies in the local group, a cluster of galaxies gravitationally bound together. The distance between them, 2.5 million light-years, is enormous. Yet it is not the largest distance between galaxies. It is actually one of the smallest significant distances between large galaxies. The local group contains about 80 galaxies, most of them small dwarf galaxies. Andromeda and the Milky Way are the dominant members, with most other galaxies orbiting one or both of them. Andromeda is approaching the Milky Way. The two galaxies are moving toward each other at a speed of about 110 kilometers per second. In about 4.5 billion years, they will collide and merge to form a new galaxy. This collision will be a cosmic event of unimaginable scale. The two galaxies will pass through each other, their stars scattering in new directions, their gas clouds colliding and heating up, triggering massive bursts of star formation. Eventually, the two galaxies will settle into a new configuration, probably an elliptical galaxy. This merger will be catastrophic on a galactic scale, yet it will likely not result in many direct collisions between individual stars. Space is so vast that even when two galaxies merge, the stars rarely collide. They pass by each other without touching, like two clouds of dust passing through each other. For us, living on Earth, this cosmic event is so distant in time that it is almost incomprehensible. 4.5 billion years is longer than the entire age of the solar system so far. It is longer than the entire history of life on Earth. By the time the Andromeda and Milky Way galaxies merge, the Sun will have died. The Earth will have been consumed, and all traces of human civilization will have been erased. Yet this event will happen. It is written in the motions of the galaxies, in the physics of gravity, in the structure of space itself. The discovery that Andromeda was a separate galaxy, made by Edwin Hubble in 1924, fundamentally changed our understanding of the universe. Before this discovery, many astronomers believed that the Milky Way was the entire universe. Andromeda was thought to be a nebula within the Milky Way, a cloud of gas and dust, not a separate galaxy. But Hubble's observations of Cepheid variable stars proved that Andromeda was too distant to be part of the Milky Way. It had to be a separate galaxy. This revelation showed that the universe was far larger than anyone had suspected. The Milky Way was not the universe, it was just one galaxy among many. After Hubble's discovery, astronomers began to realize the true extent of cosmic scale. They found galaxies in every direction, billions of them, each containing billions of stars. The universe expanded from a single galaxy to billions of galaxies. The Milky Way, which had seemed so vast, suddenly became just one galaxy among billions. Our Sun, which had seemed so important, became just one star among billions in one galaxy among billions. The perspective shifted. Humanity's place in the cosmos became smaller, but also more integrated. We were not at the center of creation. We were tiny inhabitants of a vast universe. The distance to Andromeda, measured in light years, makes this expansion of perspective concrete. 2.5 million light-years is so vast that it is difficult to comprehend. It is 250 times the distance to the nearest star. It is 100,000 times the distance across the Milky Way. No, that is not correct. Let me recalculate. Andromeda is 2.5 million light-years away. The Milky Way is 100,000 light-years across. So Andromeda is 25 times the distance across the Milky Way. It is so far away that the light from it takes 2.5 million years to reach us. Yet Andromeda is the nearest large galaxy to us. All other large galaxies are even farther away. The fact that Andromeda is visible to the naked eye, despite being 2.5 million light-years away, speaks to its incredible luminosity. It is so bright that its light, spread across 2.5 million light-years of space, is still bright enough to be detected by the human eye. This tells us that Andromeda is intrinsically very luminous, containing about 1 trillion stars. If Andromeda were farther away, we would not be able to see it without a telescope. If it were much farther away, we would not be able to see it at all. Clusters, superclusters, and the cosmic web. Beyond the local group lies a vast structure of galaxies, organized into clusters and superclusters, forming a cosmic web of unimaginable complexity and scale. Galaxies are not randomly distributed through space. They are organized into hierarchical structures held together by gravity. The smallest structures are galaxy clusters, containing tens to thousands of galaxies bound together by gravity. The Milky Way and Andromeda belong to the local group, which is itself part of a larger cluster called the Virgo cluster. The Virgo cluster is centered about 54 million light-years from Earth. It contains approximately 1 to 300 galaxies, though some estimates suggest it may contain up to 2,000 galaxies. These galaxies are bound together by gravity, orbiting around the cluster's center of mass. The Virgo cluster is one of the nearest large galaxy clusters to the local group. The space between the local group and the Virgo cluster is spanned by tens of millions of light-years. Light from the Virgo cluster takes 54 million years to reach us. When that light began its journey, dinosaurs still roamed the Earth. By the time the light reached our solar system, dinosaurs had been extinct for millions of years. Beyond individual clusters lie superclusters, structures containing multiple galaxy clusters. The local group and the Virgo cluster are both part of the Virgo supercluster, a structure spanning approximately 110 million light-years. The Virgo supercluster contains tens of thousands of galaxies organized into multiple clusters. Yet even superclusters are not the largest structures in the universe. Beyond superclusters lies the cosmic web, a structure of filaments and voids extending across billions of light-years. The cosmic web was revealed by large surveys of galaxy positions. Astronomers mapped the locations of millions of galaxies and discovered that they are not uniformly distributed. Instead, galaxies are concentrated in long filaments stretching across space, with vast voids between them. These filaments are like threads in a cosmic tapestry, linking distant clusters and superclusters. The largest structures in the universe are these filaments, spanning hundreds of millions or even billions of light-years. One famous structure is the Great Wall, a filament of galaxies spanning approximately 500 million light-years. Another is the Hercules supercluster. Yet another is the Sloan Great Wall, discovered in 2003, which spans over 1 billion light-years. These structures are so vast that their light takes over 1 billion years to cross them. They represent the largest organized structures in the universe, the result of gravity working on the primordial density fluctuations that existed in the early universe. The cosmic web is not static. It evolves over time. Galaxies move within the web, drawn by gravity toward denser regions. Clusters and superclusters form as gravity amplifies small density differences in the early universe. The web grows and changes over billions of years. When we observe distant galaxies, we are observing the web as it was in the past. By comparing nearby galaxies with distant galaxies, we can see how the cosmic web has evolved over billions of years. The existence of the cosmic web raises profound questions about the structure of the universe. Why is matter organized into filaments and voids rather than distributed evenly? The answer lies in the early universe and the physics of gravitational instability. In the early universe, there were tiny density fluctuations, regions slightly denser than average and regions slightly less dense. Gravity amplified these fluctuations. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter and became even less dense. Over billions of years, these initial fluctuations grew into the cosmic web we observe today. The cosmic web is organized on scales measured in millions and billions of light-years. A single filament might span 500 million light-years. A supercluster might span 100 million light-years. Even individual galaxy clusters span millions of light-years. These are the scales at which gravity has organized the universe. These are the scales at which the cosmic web exists. And all of these scales are measured in light-years, because light-years are the only unit that makes sense for cosmic distances. When you contemplate the cosmic web, you are contemplating the largest organized structures in the universe. You are looking at the universe's architecture, the framework on which all galaxies and stars are arranged. The cosmic web is not a random arrangement. It is the result of billions of years of gravitational evolution, starting from tiny density fluctuations in the early universe. Every galaxy, every cluster, every supercluster is part of this web, connected to other structures by gravity and the expansion of space. The cosmic web also reveals something about the universe's expansion. The universe is not expanding uniformly. Gravity holds galaxies and clusters together, preventing them from being separated by the expansion. But at larger scales, the expansion dominates. Superclusters are separated by the expansion. Filaments are separated by the expansion. The cosmic web is stretched by the expansion of space, with the voids between filaments growing larger over time. In the very distant future, the universe will become even more sparse, with filaments separated by enormous voids and individual superclusters isolated from each other by the expansion. The observable universe's edge. At the largest scales, we encounter a profound boundary, the edge of the observable universe. This is not the edge of the universe itself, but rather the edge of the region we can observe. The observable universe has a radius of approximately 46.5 billion light-years. This is larger than 13.8 billion light-years, which is the age of the universe because space has been expanding throughout the universe's history. Light from distant regions has been traveling toward us for 13.8 billion years. But during that time, those regions have also moved farther away due to the expansion of space. The result is that the farthest observable objects are about 46.5 billion light-years away, even though the universe is only 13.8 billion years old. The observable universe is a sphere centered on Earth. This does not mean that Earth is at the center of the universe. Every observer in the universe, looking out from their location, sees themselves at the center of their own observable universe. The observable universe is defined by the distance from which light has had time to reach us since the Big Bang. It is a boundary defined by light travel time and the age of the universe. Beyond the observable universe lies the unobservable universe, a region so distant that light from it has not yet had time to reach us. We cannot see this region. We cannot know what it contains. In principle, the universe might extend far beyond what we can observe. It might be infinite. It might be finite, but vastly larger than the observable universe. We may never know. The observable universe is the limit of human knowledge about the cosmos. The farthest objects we can observe are the most distant galaxies, detected by powerful space telescopes. These galaxies are so far away that their light has been traveling through space for over 13 billion years. When we observe them, we are seeing the universe as it was in its infancy, only a few 100 million years after the Big Bang. These early galaxies look different from nearby galaxies. They are smaller, less structured, and more chaotic. They are undergoing rapid star formation. They are the building blocks from which today's galaxies evolved. The discovery of these distant galaxies has revolutionized our understanding of cosmic history. By observing galaxies at different distances, and therefore at different times in cosmic history, we can watch how the universe has evolved. We can see young galaxies in the early universe. We can see middle-aged galaxies at intermediate distances. We can see old galaxies nearby. We can watch, in a sense, how galaxies grow, merge, and evolve over billions of years. This is the power of looking at distant objects. We are looking at the past, and we are seeing cosmic history written in light. The edge of the observable universe is defined by the cosmic microwave background, the oldest light in the universe. This is radiation left over from the Big Bang, emitted about 380,000 years after the universe began. For the first 380,000 years, the universe was opaque, filled with a hot plasma that scattered light. After 380,000 years, the universe cooled enough for electrons and protons to combine into neutral atoms. The universe became transparent, and light could travel freely. The light that was released at this moment has been traveling through space ever since, continuously redshifted by the expansion of the universe. Today, this ancient light appears as the cosmic microwave background, radiation coming from all directions with a temperature of about 2.7 Kelvin. The cosmic microwave background represents the edge of the observable universe in time. We cannot see farther back in time than this because the universe was opaque before this moment. We cannot see the first 380,000 years of the universe's history with light. We can only infer what happened during this period from theoretical models and from the patterns we see in the cosmic microwave background. The cosmic microwave background is the oldest light in the universe, and therefore the farthest back in time we can look. The distance to the cosmic microwave background is approximately 46.5 billion light-years, the radius of the observable universe. This light has been traveling through the expanding universe for 13.8 billion years, and during that time, the region from which it originated has moved even farther away due to the expansion. The result is a distance of 46.5 billion light-years. This is the edge of what we can observe. Beyond this boundary lies the unobservable universe, forever hidden from our view by the limitations of light travel time. The observable universe contains approximately 200 billion galaxies, each containing billions or trillions of stars. The observable universe spans approximately 93 billion light-years in diameter. These numbers are incomprehensibly large. The human mind cannot truly grasp them. We can calculate them, we can write them down, we can contemplate them intellectually, but we cannot really understand them in an intuitive way. They are beyond the scale of human experience. Yet these are the true scales of the universe. These are the distances that separate us from the farthest galaxies. These are the scales on which gravity has organized matter. These are the scales that define the cosmos. When we measure these distances in light years, we are measuring them in the only unit that makes sense. Light years acknowledge that the universe operates on scales where light itself takes billions of years to cross from one side to the other. Light years make the incomprehensible slightly more comprehensible by translating distance into time, a dimension that humans have some intuitive understanding of. Time, light, and the nature of observation. The concept of a light year reveals something profound about the relationship between time, light, and observation. When we measure distance in light years, we are not merely choosing a convenient unit. We are acknowledging a fundamental truth about the universe. Distance and time are linked through the speed of light. Observing something distant is observing something from the past. The farther away something is, the older the light you receive from it. This is not a limitation of our telescopes or our technology. It is a fundamental property of the universe. This connection between distance and time has deep implications for how we understand reality. In everyday life, we think of the present as a moment that exists simultaneously everywhere. We imagine that events happening right now in a distant city are truly happening now, even though we cannot see them. But in relativity, this notion of a universal present moment does not exist. Different observers in different locations disagree about what events are happening now in distant regions of space. The light year reveals this truth. When we measure distance in light years, we are acknowledging that the present moment is not universal. What counts as now depends on where you are. Consider what it means to observe a distant star. The light from the star has traveled through space for years, decades, or centuries to reach you. During this journey, the star itself has changed. It may have moved to a different location. It may have changed in brightness or color. It may have exploded in a supernova. You have no way of knowing what has happened to the star in the time since the light you are observing left it. You can only see the star as it was when the light began its journey. You are always looking at the past. This fundamental fact about observation has profound implications for our understanding of causality and the arrow of time. Events that happen to distant objects can only affect us after light from those events has traveled to us. We cannot be affected by distant events in the present moment. We can only be affected by events that happened in the past, events from which light has had time to reach us. This is the principle of causality. Causes precede effects, and effects cannot propagate faster than light. Light years reveal the structure of causality in the universe. They show us the light cone of events that can causally affect us, and the light cone of events we can causally affect. The act of observation also raises philosophical questions about the nature of reality. Does reality exist independent of observation, or does observation somehow create reality? This question, which has puzzled philosophers and physicists for centuries, takes on a new dimension when we consider light years. When we observe a distant galaxy, we are observing ancient light. That light has been traveling through space for billions of years. The galaxy has evolved and changed. It may no longer exist, yet the light we observe carries information about how the galaxy was billions of years ago. We cannot know the galaxy's present state. We can only know its past. This introduces a fundamental uncertainty into our knowledge of the distant universe. Some physicists have argued that observation itself plays a role in determining reality, based on the quantum mechanical principle that the act of measurement affects the system being measured. In quantum mechanics, particles exist in a superposition of states until they are observed, at which point they collapse into a definite state. This principle, called the measurement problem, has led some physicists to suggest that consciousness or observation plays a fundamental role in creating reality. However, this interpretation is controversial, and most physicists believe that observation simply reveals aspects of reality that existed before the observation. The light year also reveals something about the limits of human knowledge. We can never know the present state of distant objects. We can only know their past. We can observe ancient light and infer the properties of distant objects at the time the light was emitted. But we cannot know what those objects are like now. The universe is hidden from us by the finite speed of light. Light years measure this hiddenness. They measure the distance between us and the objects we observe, and they measure the time that separates the light we see from the events that produced it. This temporal separation between observation and event is not something we typically experience in everyday life. When you observe a nearby object, the light takes an insignificant amount of time to reach your eyes. You see the object almost instantaneously as it is. But when you observe a distant star, you see it as it was years or centuries ago. The temporal separation becomes significant. The light year makes this temporal separation concrete. It expresses distance in units of time, making it clear that looking far away is looking far back in time. The relationship between light, time, and observation also has implications for how we understand the expansion of the universe. The universe is expanding, and distant galaxies are receding from us. The farther away a galaxy is, the faster it is receding. This is Hubble's law, discovered by Edwin Hubble in 1929. When we observe distant galaxies, we see them as they were in the past, when they were closer to us. We are observing the universe's past expansion. We see young galaxies in the early universe, when the expansion was rapid. We see older galaxies nearby, when the expansion had slowed. By observing galaxies at different distances, we are observing the universe at different stages of its expansion. We are watching cosmic history, living within light years, a meditation on scale. As we conclude this exploration of light years and cosmic distance, let us reflect on what it means to live within a universe measured in light years. We are creatures bound to a small planet orbiting an ordinary star in a vast galaxy. The nearest star is 4.24 light-years away. The nearest large galaxy is 2.5 million light-years away. The observable edge of the universe is 46.5 billion light-years away. We are surrounded by distances so vast that light itself takes billions of years to cross them. We are trapped within these distances, unable to traverse them in any reasonable time frame. Yet we have developed the ability to observe across these distances, to see the ancient light of distant objects, and to understand something of the universe's structure and history. This is a remarkable achievement. We are small, short-lived creatures on a small planet, and yet we have figured out how to measure the universe. We have discovered that light takes years to travel between stars, and we have created a unit of distance, the light year, that expresses this fact. We have pointed telescopes at the sky and observed galaxies so distant that their light took billions of years to reach us. We have seen the universe as it was in its infancy. We have understood something of how the universe is structured, how gravity has organized matter into galaxies and clusters and superclusters, how the universe has evolved over billions of years. The light year is a humble unit. It is simply the distance that light travels in 1 year. It is defined by a physical constant, the speed of light, and by a unit of time that we have defined, the year. Yet this humble unit reveals something profound about the universe. It reveals that distance and time are linked. It reveals that observing distant objects is observing the past. It reveals that the universe is vast beyond human comprehension, yet comprehensible to human intellect. We may not be able to truly grasp the size of a light year, but we can contemplate it. We can calculate with it. We can use it to navigate the cosmos with our minds. Living within light years means living within a universe where the distances are incomprehensibly vast. It means that we are isolated from other stars and galaxies by these vast distances. It means that we will never be able to visit the nearest star, let alone travel to other galaxies. The fastest spacecraft humanity has ever built would take 64,000 years to reach Proxima Centauri. No human will ever make this journey. We are bound to Earth by the immensity of space. Yet this isolation is also a gift. It has allowed life on Earth to evolve in its own way, without interference from other worlds. It has allowed human civilization to develop without contact with alien civilizations. We are alone, but we are alone in a vast and beautiful universe. The light year also reminds us of the age of the universe. The universe is 13.8 billion years old. Light from the edge of the observable universe has been traveling for 13.8 billion years to reach us. This is an incomprehensibly long time. It is longer than the entire history of life on Earth, longer than the existence of the solar system, longer than the existence of the Milky Way. Yet the universe is even older in some sense. The observable universe has a radius of 46.5 billion light years, because space has been expanding throughout the universe's history. Regions that emitted light 13.8 billion years ago are now 46.5 billion light years away. The universe has been stretching, expanding, growing for 13.8 billion years. When we contemplate light years, we are contemplating time as well as distance. We are contemplating the age of the universe, the history written in light, the vast stretches of time that separate us from distant objects. A light year is not just a distance, it is a duration. It is a measure of how long light takes to cross a distance. It is a measure of cosmic time. When we say that something is 1 billion light years away, we are saying that light from that object took 1 billion years to reach us. We are saying that we are observing something that happened 1 billion years ago. We are looking at history. Living within light years means living within a universe where time and distance are linked, where observing is always observing the past, where the present moment is not universal, but relative to the observer. It means living in a universe that is far larger and far older than human civilization. It means living as a conscious being aware of this vastness, capable of understanding something of the universe's structure, even though we are so small within it. This awareness can be humbling. It can make us feel insignificant, like tiny specks in an incomprehensibly vast cosmos. But it can also be elevating. It can remind us that we are made of the same atoms that were forged in the hearts of distant stars. We are part of the universe, observing itself. We are the universe, conscious and aware. The light year invites us to contemplate our place in the cosmos. We are not at the center of the universe. The universe does not revolve around us. We are inhabitants of a small planet orbiting an ordinary star in a spiral arm of a large galaxy among billions of galaxies. Yet we are here. We exist. We are conscious. We have developed the ability to understand something of the universe's structure and history. We have created the light year as a tool to measure distances that our minds cannot fully grasp. We have pointed telescopes at the sky and observed the universe's ancient light. We have wondered about our place in the cosmos and have found peace in the contemplation of vast distances and vast times. This journey through light years, from the speed of light to the edge of the observable universe, is a journey through the structure of reality itself. It is a journey that reveals the deep connection between space and time, between distance and history, between observation and the past. It is a journey that shows us how the universe is organized, how gravity has shaped matter into structures ranging from planets to galaxies to superclusters, how the universe has evolved over billions of years. It is a journey that reminds us of our smallness and our significance, of our isolation and our connection to the cosmos. Thank you for joining me on this exploration through light years and cosmic distance. If this journey through the incomprehensible scale of the universe has brought you wonder and peace, I would deeply appreciate a like and subscription to the Relaxing Science channel. Your support helps us continue to explore the mysteries of the universe and to share these explorations with others who seek to understand the cosmos. Also, I would love to know, where are you listening from and what time is it where you are? Share your location and the time in the comments below. Your presence here in this moment is part of the vast tapestry of consciousness experiencing the universe. As you move through your day, carry with you the knowledge that you are made of atoms that were forged in distant stars. You are observing the universe from within itself. You are the cosmos, aware and wondering, contemplating the incomprehensible distances that define existence. May you find peace in this awareness, and may your curiosity about the universe continue to grow. Until next time, keep looking up at the stars and remember that the light reaching your eyes has traveled across vast distances and vast times to connect you to the distant cosmos.